So before we actually solve the conundrum that was posed in the last video segment, let's take a detour on the wave equation. So let's take a detour on the wave equation. So why do I call it the? Why is there like a scare quotes? And the reason is that the wave equation that we are going to discuss is the typical wave equation that one comes across. But it is by no means the only wave equation. There are many different wave equations in physics, but we are just going to discuss one. It's not going to be the wave equation that turns out to be the Schrodinger equation, but discussing it will lay the groundwork for what we have to understand for the Schrodinger equation. So let's consider a one-dimensional problem. So let's consider like a taut string. And let's consider small oscillations of a taut string. So we have a string which is, say, extended in the x direction, and it's oscillating in the y direction. And let me just magnify everything. So this is the string. I take a very small element of the string, an infinitesimal element, and then so you can show that for such a string, for small vibration, the tension in the string, which is in this direction and this direction, the tension in the string is approximately this constant. So let's introduce some parameters. So the angle that the tension here makes with the x-axis is theta, and the angle here is going to be theta plus delta theta. And this is the x value, and here we have the value is x plus delta x, and this is y, and over here, this is going to be y plus delta y. Okay, and let's also take this the string to have uniform density. So this is going to be, mu is going to be the linear density. So it's going to be the mass of the string per unit length. Okay, so so what's the force on this string? So, as we can see in the x direction, the force is going to be, so, over here we have the tension, going in the positive direction. Here the tension is going in the negative direction. So we have t cosine of theta plus delta theta minus t cosine of theta. And in the y direction, the force in the y direction will be t sine of theta plus delta theta minus t sine of theta. So let's assume that the oscillations are very small, so that theta and delta theta both are very small. And if you do this, then these two equations become, the first equation just becomes a trivial equation, because for small value of the argument, the leading value of cosine is 0. But the second one, what I get is, I get t delta theta. So now we apply Newton's law to this non-trivial equation. So Newton's law is, the force is t times delta theta, and this is in the y direction. So it's going to be the mass of that element, which is going to be mu times delta x, and the acceleration in the y direction is going to be ay. So this is our dynamical equation. So we want to turn this into a differential equation. So let's go back to our diagram, and if I look at how what the angle theta is in terms of how, say, this thing varies, x varies with respect to y, then of course we're going to have that tan of theta will be given by dy by dx. Now we can take the derivative of this equation with respect to x. So if I take the derivative with respect to x, so derivative, so with respect to x, then using the chain rule, we get that this is going to be sec squared of theta, and then we have d theta by dx, but I'm just going to write this as delta of theta, and I'm going to take the delta x to the other side, and here we have a second derivative times delta x. Okay, now in this equation, in our main equation over here, what we see is that delta theta, it varies. It's due to the change in theta is due to the change of y with respect to x, but at fixed time. So this is basically frozen in time, this picture. Whereas on the right hand side, this guy is the variation, is the derivative of of y with respect to t, but for fixed x. Of course, this is the second derivative, but the idea is that the x here is fixed and here the t is fixed. So we're going to get from this a partial differential equation. That's the whole point. So now what I do is that I take this equation and I take theta to be small. If I take theta to be small, then what I get is, this thing is just 1. Then I get, this is going to be del squared y, del x squared, del x, right? So now what I do is that I use this to replace del theta in this equation. If I do that, then I get on the left-hand side t del squared y, del x squared, delta x, and on the right-hand side I had mu delta x and y. Ay is the acceleration, which is nothing but delta squared of y, delta t squared. All right. So now this thing, delta x cancel out, and therefore we get from this equation the equation that we were looking for, which is delta squared y, delta x squared is mu by t delta squared y, delta t squared. So this is the equation that we were looking for, but let's make another observation. That the dimension of this thing is that of 1 over speed squared. So therefore, we can write, this equation that we derive in the following form. We can write this as del squared y, del x squared is equal to 1 over v squared, del squared y, del t squared. And this is our wave equation in one dimension. Okay, 1 plus 1 dimension.